This is Free Range Digital Design Foundation Modeling, Chapter 13. What we're going to be doing in this chapter is a small subset of binary mathematics. By all means, computers are known for doing mathematics, so this is our introduction to computer mathematics. We'll be limiting ourselves to addition and subtraction, and more details on that later. Computers are known for doing mathematical operations, and computers also known for the fact that they do everything in binary. Computers do a lot of things. There are a lot of different binary representations of numbers, which the computers are going to crunch, and I don't pretend to know all those forms. So this is an introductory course, and we're going to be working primarily with just two of those forms, which is unsigned binary and signed binary in RC format. Now, this is a really limited approach, but it'll give you a solid foundation, and we can go from there. In terms of mathematical operations on computers, what you're interested in is having your hardware give you the correct result. And in our context, that means a valid result. Now, that means we have two basic approaches to ensure we get a valid result. And one of those approaches is to make your hardware so big that no matter what the size of the inputs are, it will always generate the right answer. So this means extending the data widths as far as possible. But when you extend the data widths in terms of the underlying hardware, you're increasing the size of that hardware, which increases its complexity, increases its power consumption, and typically not a super great idea unless you have a really good reason to do such. So the approach we're going to be taking is to use a reasonable amount of hardware, which essentially means limited data widths. The idea here is the answer may not always be valid, but we have to have a method to detect whether that answer that the computer gives us is valid or not. And if it isn't valid, possibly have some strategy to make it valid or indicate that it's not valid. The trade-off here is less hardware, which is a savings, but then we're going to have to do some type of checking to ensure the answer is valid. So we've been doing addition with unsigned binary using a ripple carry adder, and we'll continue to do that, but now we have signed numbers, and we want to introduce the notion of subtraction. One approach we could take on this is to start from scratch and design a subtractor module, which is valid, but we're not going to do that. So we're going to take the approach of using that ripple carry adder, that adder module we already have, that adds, of course, and we're going to use that as a subtractor. And the way we're going to do that is with this formula here, which is essentially referred to as indirect subtraction by addition. So the idea here is using radix complement, which is 2's complement format, we could very easily change the sign of a value in hardware. So we didn't really do anything in hardware, and we're really not going to do anything in hardware yet, but it's a simple operation to change the sign of any value. And the way you do that is you toggle all the bits and you add 1. Essentially you can say minus a equals a bar plus 1. Okay, so an a could be a bus on this thing. So the idea here is we're essentially going to change the sign of it, then add it, and that's going to be equivalent to subtraction. That's how we're going to handle subtraction in this course. We're not going to necessarily design a subtractor module. Computers have fixed data widths, as we discussed a little bit earlier, which means there's limits on the math operations you can do on a computer. Because of the fixed hardware, not infinite data widths, we're going to have to do a couple things. Number one, we're going to have to check our result and see if it's valid. The validity checks, there's not like one validity check for every operation. There's going to be multiple validity checks, and if we discover the result is not valid, there's the option of what to do about it. One is design hardware to make it valid. Other is just have some type of signal that indicates the given result is not valid. So the approach we're going to take is have a signal that indicates the approach is not valid. There may be a problem where we try to adjust it and make the result valid based on some conditions, but we generally don't go there. We're more interested in, is the result valid or not? Validity has to do with the number ranges of the formats you're working with. And so these were our number ranges from a previous chapter, and this is example 8-bit ranges. The issue here is if my result falls into this range, it's okay, but if it falls out here or out here, it's not valid. And the same with signed binary radix complement form. If the result's in here, it's okay. If it's out here, it's not valid. And we're going to design checks to find those conditions. So we have two different types of validity checks. So one is for unsigned binary, which we're constraining to only do addition. The other one is for signed binary, which we're going to allow ourselves to do both addition and subtraction. For unsigned binary, we're going to use a ripple carry adder. The idea here is if we do operation, an add operation, and that operation generates a carry, which means the carry out is a 1, that we're going to consider the n-bit results coming out of that ripple carry adder to be not valid. Now in theory, the carry out represents the nth plus 1 bit. It's actually sort of valid if you could consider that, but what we're interested in is the carry out is set. That means the bits in the sum are not correct. They will have a value there, but it does not reflect the addition of the two input operands. For radix complement, it's a little bit different, where we don't really care about the carry out, completely separate issue. What we care about is the sign of the two operands and the sign of the result. When we talk about the signs of the operands and the result, there's 3 different sign bits that we're interested in. So that means we have, technically speaking, we have 8 different possibilities, which is 2 to the 3rd, 3 coming from the 3 sign bits. 8 different possibilities of, pluses and minuses, whether the bits are set or not. And of those 8 possibilities, 2 are invalid. And so I'm going to list those here and talk about those, but not go too far into it. We will more so delve into this via examples. So the 2 invalid cases are when these are the 2 invalid cases. I know the answer is invalid when the signs of the inputs are the same but different from the signs of the output. These are the 2 special cases where it's invalid. All the other cases are going to be valid, particularly when I'm adding 2 numbers of different signs. The magnitude is always going to shrink. The result is always going to be within range. Those values will always be valid. These are the only cases that I'm looking for that indicates the answer on the sum output of the ripple carry adder is not valid. So these are some examples of addition for unsigned binary. I'll go ahead and add these up. So these are both, they're all positive numbers, so I'm just going to add them directly. I don't have to worry about changing them. So this is just straightforward binary long addition. There's a 0, carry the 1, 0, carry the 1, 0, carry the 1, 1. There's no carry out on this thing, and this is going to be valid. Second one, 0, 1, 1, 0 plus 1, 0, 1, 0, 1, 0. That's going to be 0. So 0 is a 0. 0, carry the 1. Carry the 1, 0, carry the 1. Okay, here's my carry out. It's set. So what that's saying is this answer here, these 4 bits are not valid. I mean, they're valid bits, but it doesn't reflect the sum of the 2 inputs. Okay, so the last example here, we have 1, 1, 0, 0 plus 0, 1, 1, 1. So that's 1, 1, 0. Carry the 1, 0, 1. Once again, we have a carry, which indicates that these bits right here are not valid. These are some examples of addition and subtraction using radix complement, 2's complement format. For this A example up here, I'll do it up here because I'm going to run out of room. 0, 0, 1, 1 plus 0, 0, 1, 0. I don't need to take any 2's complements on these things. They're both positive numbers. I'm doing addition. No need to do anything special here. That's a 1, that's a 0, carry the 1, 1, 0. So that looks good. If you look at that, it's 3 plus 2, which is in fact 5. So this is a valid. And notice that the sign of the 2 inputs is positive, the sign of the result's positive, that's okay. That indicates it's valid. So B, I have 0, 1, 1, 0 plus 1, 0, 0, 1. Add these up and get 1, 1, 1, 1. And the notion here is that we got two values of different sign. When I add those together, it's always going to be valid. So this is also valid. So this is an example here where I need to do some extra work on this thing. 0, 1, 0, 0. But I'm subtracting minus 0, 0, 1, 1. So I don't know how to subtract, but what I do know how to do is I'm going to take the 2's complement of this and add it. So here's the 2's complement of that number, 1101. I'm going to add it. 1. I can see already that it's going to be valid because I'm adding a positive and negative number. No big deal to do this addition here. 0 plus 0, 0, 1 plus 1, 0, carry the 1, 1 plus 0, 0. And there's going to be a carry out. Okay, so here's a carry out. Carry out has nothing to do with this technique. There's things you can do with the carry out, but we're opting not to do anything with that carry out. So once again, I'm adding a positive and a negative number. This is always valid. Okay, so lastly here, I got 0, 1, 0, 0. And I'm subtracting 1, 1, 0, 0. I don't know how to subtract, but what I do know how to do is take the 2's complement of it and add it. So this is going to be, this is what I'm going to add. This is the 2's complement. Together, 0, 0, 0, and carry the 1, 1. And there's no carry out, but check it out. I'm adding two numbers, two positive numbers. I'm getting a negative result. Everything's based on 4 bits. Sure, there's a carry of 0 there, but that's completely ignored. Even though there's no carry out on this thing, it has nothing to do with this technique. The only thing I care about is the sign bits of the data width. I'm not considering that carry out to be part of the data width. Add two positive numbers, get a negative number. This is not valid. Okay, so there's a special case that I didn't say anything about, and I pretty much ignore it for this entire course, but when you're working with RC numbers, there's another case that's invalid. And the problem is we have a validity check for RC numbers, but it fails in one case. And the case it fails in is when you are subtracting the largest negative value. And essentially that's it. When I'm subtracting the largest negative value, it's going to fail. And technically speaking, I should include that in our check, but I actually just don't go there. It's a little bit troublesome. It's easy enough to design in the hardware, but it's even easier to kind of ignore. But I want to make you aware of this. There's one case where our fairly simple intuitive validity check fails, and you might run into that case, so just be aware of it.